Hello, welcome everyone. Sorry I couldn't attend this conference in person, and I hope everyone's having fun in Australia listening to all the talks. My name is Shivam Bharuka. I'm a production engineer in the AI infrastructure team at Meta. Today, I'll be talking to you about the ML training infrastructure stack and how we operationalize it at the scale of Meta itself. So before we get started, let's look at the use cases of machine learning at Meta. As we know, machine learning is everywhere. Most major Meta products and services leverage machine learning today. For example, newsfeed ranking algorithms use machine learning to help show the relevant stories to the users of our platform. Ads leverages machine learning to determine which ads to display to a given user. Similarly, language translation helps any post to be translated from any language to a language of the user's choice, and site integrity helps identify bad actors on the platform. There are so many more use cases like these which are used and leveraged by our services at Meta. So how do these machine learning models get deployed and how are they executed? There are three major steps in any machine learning pipeline. You start with data preparation, which is basically a combination of collecting data from different platforms and processing it to store it in formats which we call as features. Once these features are available, we train a model. Either a model is trained from scratch or a new mod or an existing model is refreshed on new data. Once the model is trained, it's validated on additional data to ensure that the quality of the model is good. And then it is deployed into production, where it's performing real-time recommendations, rankings, translation, and so on. Today, I'll be focusing my talk on the model training part of this life cycle. This is one of the most important part of any machine learning deployment process, and is responsible for the accuracy and the performance of the model itself. So let's look at the given today's trend in terms of machine learning training. The current trend is to train larger and larger models. Train them as fast as possible, and you have to prepare for an unknown future. Machine learning models are changing every day. You might have a different kind of an architecture today from what you have in a year or in 3 years or in 5 years. So you have to design your systems with that unknown future in mind. You need to come up with novel system design that can fit the entire problem space given the size and the latency requirements of these models itself. What does this mean? This means that we need to take a holistic approach in designing both the software and the hardware together and revamping them such that they can accommodate for such characteristics. So how do we do it? What we'll do is we'll look at both the hardware side and the software side. What are the challenges in deploying those? How do we deploy them at Meta? And talk about some of the reliability practices that we have taken to ensure that we are running a healthy and scalable platform. So let's start with the hardware. AI hardware is more complex than compared to any CPU based architecture. You have complex accelerators such as GPUs and ASICs. So these GPUs, which are provided by NVIDIA, or special accelerators, which are created in-house by different companies, such as like Google has TPUs in their data centers. Similarly, Facebook is working on their inference accelerator and training accelerators. These are present in any AI hardware. These are much more complex compared to any CPU machine. As you can see in the diagram on the presentation itself, a single server has 8 accelerator chips, 4 CPU chips, a bunch of network cards, and SSDs and memory cards in a server itself. Compared to a CPU system where you just have 1 or 2 CPU, this means that the number of shared paths in any server of AI hardware is much more compared to a generic CPU architecture. You have multiple layers of network. You have the front-end network, like any traditional CPU server, which is used to connect to the data center. You have multiple layers of back-end network to facilitate communication inside a node, to communicate between the 8 accelerators or the GPUs inside the server itself. and then layers of network to communicate with other hosts inside your data center. This is a separate line of communication which is deployed to facilitate accelerator to accelerator communication. Apart from this, you have these nodes deployed at the DC scale. We have special zones in our data center where such nodes are deployed at scale and are connected together using the layers of network, which I just mentioned. These systems are also very tightly coupled. A failure or a drop in one of these network backends leads to a failure in across the entire job itself. And the network requires lossless behavior because of the requirement of how AI training is done. AI training requires that each GPU talks to each other to share their learnings, and high bandwidth network requires the lossless behavior, which I just mentioned. So when we are designing such a AI hardware, what are the challenges which comes with it? The challenges are across the entire life cycle of the server itself. You start at supply, you go through the integration, you do quality assurance, and then you have to maintain it in production. So let's look at the challenges at each phase of AI hardware. Let's start with supply. In terms of supply, you need to source and assemble these complex machines with multiple parts. Compared to a traditional CPU, you have 3x to 5x replaceable units in AI hardware itself. So what is the metric that we use to ensure that supply and assembly is not our biggest challenge? We, from each of our suppliers, we take a commit against the demand which Meta has across multiple quarters. And we ensure that the commitments are met at a P90 or a P95 level, such that we can de-risk the capacity requirements and the demand requirements we have in the coming quarters. Apart from looking at this metric, the step we have taken to de-risk this part of the life cycle is we have contracted with multiple vendors, and we perform resource planning much in advance. We plan for the next year and even more, such that we can ensure that the supply and assembly is not our biggest constraint. The next step is the system integration step. You have to do multiple enablements. AI hardware has to go through enablements of the kernel. If you're getting NVIDIA GPUs, you have to enable the GPU drivers. You have to do testing at the node layer, rack layer, and at the cluster layer, which are at DC scale itself. So the metric we use to track this is time to production. Once we land a machine from our supplier in our data center, we measure how much time does it take for us to get it into the hands of our customer itself. And we optimize for this time to production. One of the efforts we have taken to minimize time to production itself is we perform early testing during our NPI process. NPI process is the process which we use to take any machine and bring it to our data center into our hands of our customer itself. We perform early testing during this process, and we have taken a hard look on how to parallelize each of these different system integration components which are needed in the system to bring AI hardware to our users itself. Next is quality assurance. Once the hardware is available to our users, we want to ensure that the hardware is healthy and it can be used by the users in a reliable fashion itself. But the challenge is the probability of failure. Due to the sheer number of parts, due to the complexity of the network, due to the lossless behavior which is needed to run ML models, the probability of failure is much higher. And the layer of complexity makes it even more challenging. So the metric which we measure here is the failure rate. Like I mentioned in the previous step, we perform early testing during our NPI process. During each of these phases, we also measure the failure rate or the quality of the system itself. The time to production is not the only thing matters. The quality is also what we really care about. And one of the efforts that we have taken in order to optimize for this is we have developed a new suite of benchmarks which can help us detect failures early in the NPI cycle. We know that the current benchmarks that we have for CPU system don't really pan out for AI hardware. We need to test the network and stress it in multiple ways. The new suites of benchmarks is something which has helped us accelerate this. We have even shared these benchmarks with our ODMs and our suppliers such that they can perform testing at their stage before even handing over the hardware to us. This helps us get even earlier signal before getting the hardware into our data center itself. The last step is maintaining the hardware in production. Once the hardware is handed over to our customers, we want to ensure that it stays healthy. The biggest challenge here is that we do not have enough systems to detect failures and repair them. What we noticed in our data center is AI hardware used to go to repair and come back and then go again. Like it used to be in a loop. This was due to the lack of the tools which we have to repair such systems. When we detect a hardware is bad due to a network issue, we send a particular host to repair. Maybe that host is not bad. Maybe we need to test the network at the cluster layer to identify what is going wrong with the system. So we have come up with two metrics here. Availability, which is a common metric used in data centers to measure the health of the servers, and mean time between failures. We really look at how much time does a hardware stays in production at an average, because we want to ensure that these hardwares are not going in and out of repair. And a step we have taken to ensure that the failures are detected and the repairs are done is we perform early hardware failure detection. Before running any job on these machines, we run a failure detector system every time before spinning up those jobs, such that we can test the network, we can test the GPUs or the accelerators on the machine and ensure they are healthy before running the actual job and users seeing a pain due to the quality of the hardware itself. This has helped us detect failures faster. And similarly, we have invested into our repair system such that we can detect network and higher level issues such that we don't send the hardware without fixing it back to production. Now, apart from the hardware, AI software also has very unique properties. It requires gang scheduling, which means that the trainers which are scheduled for one single jobs in any AI job itself need to work in a synchronous fashion. A failure in one node leads to a restart of the entire job itself. This is not typical of a distributed system. A failure can be tolerated at a node level. This is not the case for machine learning. Next one is we need to support multiple authoring frameworks. We have frameworks based on PyTorch. We have frameworks based on top of PyTorch, which abstracts away different modules of PyTorch. And then we have legacy Cafe 2 systems. We have multiple teams having their own authoring framework itself. So all of these frameworks and their different properties need to be supported by the AI infrastructure team itself. Next is we need to co-locate the data and compute together. Given the size of ML data, which is used to train a model itself, it is not easy or advisable for us to replicate this data across data centers. We need to design systems such that we can find out where a particular machine learning model will be scheduled and make sure that the data is present in that data center itself. So the co-location needs to happen. We need to ensure we need to accommodate for large checkpoints. A machine learning model takes checkpoints regularly to ensure that the progress is recorded. Since a model trains for a long time and can have multiple failures, we don't want to restart training after every failure. As we know, due to gang scheduling, the entire job needs to start. So we take checkpoints. These checkpoints can be huge. They increase as the size of the model increases itself. So we need to accommodate for that in our infrastructure. Similarly, we need to support for multiple generations of these machines. Every year, NVIDIA comes up with a new GPU machine. We have new accelerators being designed inside the company itself. So multiple of these different types of machines need to be supported by the infrastructure. Every time a new generation is brought to the data center, we cannot pivot all our workflows to use that. These AI hardware systems are very expensive. We want the previous generation to be utilized as well. So that challenge also needs to be addressed by the AI software. So let's look at scheduling itself. As I mentioned, there is a proliferation of machine types, and you need to co-locate compute and data together. Even apart from like co-locating data and compute, the readers, the storage IO, ensuring that there is not cross TC and cross region network bandwidth being utilized. All of these are constraints before a job can be scheduled. So what we see is that compared to any traditional distributed system, which is a scale-out system, ML training jobs are more of a scale-up problem. You need to execute them in smallest number of fault domain. The metric we use to monitor the scheduling success rate is the allocation success rate itself. And we have designed our systems to accommodate for different challenges which comes with scheduling. The first one is resource-based allocation. Instead of allocating at a machine level or a machine type level, we let users specify how much memory, how much CPU, and different resource-based constraints that they need for a particular job. And then we find the right type of machine, which is in our data center, which is even underutilized to schedule that job itself. This helps us keep the utilization of machines across multiple generations to be high. And then we have also designed a data replication system, which looks at the patterns of jobs being scheduled in different data centers and replicates jobs and plans for it in advance. The next one is job execution itself. As I mentioned, you have a gang scheduling semantic required by ML training job. This means that a failure in one of the nodes in a particular job leads to a restart of the entire job itself. This is not ideal, and this leads to a bunch of challenges in terms of debugging, in terms of impact to the job itself. The metric which we have created here is called wasted time due to failure metric. What this metric does is every time we have a failure, it measures how much extra training time needs to be spent once we restart training from the last checkpoint. So the time, which is the training time, which cannot be recovered, which is the time from the last checkpoint, which will be used for recovery to the time of failure, is measured for each of these failures. This helps us see which failures leads to an impact on the training job at what scale, and then optimize accordingly. The efforts we have taken here are multiple. We have implemented an on-demand checkpointing system based on preemption of nodes. In a typical data center, nodes have to be taken away for kernel upgrades for regular maintenance. So we have implemented a system such that a training job can be alerted in advance before one of their nodes need to be taken away for repair. This helps us take a checkpoint, take a checkpoint on demand, and then shut down right after it to ensure that the wasted time due to that preemption is negligible. Apart from that, we have implemented a batch maintenance system. So, since multiple nodes can be preempted at different times due to kernel upgrades, we don't want a job to go through multiple failures due to a single upgrade cycle itself. We batch the maintenance across a domain such that multiple nodes can be upgraded together, and a job only suffers through a preemption failure a single time during a single upgrade cycle. And the last one is implementing single node fault tolerance. As I mentioned, the trainers are not fault tolerant today. A failure in one node leads to a restart of the entire node itself. What we have done is the readers which are responsible for feeding these trainers with data, we have implemented them to be fault tolerant. This helps us ensure that the failure domain is smaller compared to before. This has helped us optimize for wasted time, which happened due to this failure significantly, and has helped us save multiple megawatts of power in our data center itself. But this is not the end. Given these efforts, with the scale of hardware and software which we have designed in our data center, we have been able to optimize training by 40x in the last 2 years. And we are able to train parameter models, where 12 trillion parameter models today in our data center. In a few years, we are targeting to go even 100x to 1000x scale in terms of both model size and complexity. That is going to come up with challenges at both hardware and software layer. And we are constantly looking at our reliability metrics at the data to figure out where we want to invest and how we want to invest to improve these underlying systems. Thank you.